We know that coupled cluster methods are highly reliable for theoretical estimation of molecular properties. The most common variants are CCSD and CCSD parenthesis T. And in fact, CCSD parenthesis T generally referred as the gold standard of the completion of chemistry. However, the high computational cost of CCSD and especially CCSD parenthesis T limit their applications to large chemical systems. There have been many attempts to development of reduced cost electron correlation methods. Some of these studies take advantage of the locality of molecular orbitals, which is based on the idea that dynamic correlation is a short-range phenomenon. Nowadays, there are many variants of the local CC methods, such as projected atomic orbital space local CC methods and local pair natural orbitals. Other approaches combining the local correlation with fragmentation approach are the clustering molecule and divide, expand, consolidate approach. And we have another alternative approach to the steep size dependency problem. And these approaches are based on the molecular fragmentations. And various molecular fragmentation approaches have been suggested to overcome the steep scaling problem of electronic structure methods. In MF approach, a molecular system is broken up into small molecular units, and energies of fragments are combined to approximate the energy of the entire system. Although the logic behind all fragmentation approaches is similar, the formation of fragments and the combination of the fragment energies differ significantly from method to method. There are many variants of the molecular fragmentation approach, such as molecular tailoring approach, fragment molecular approach, molecular fractionation with conjugate caps, systematic molecular fragmentation, and so on. However, some of these fragmentation approaches are designed for specific molecular systems. Some of them are designed for the molecular cluster. Some others are just designed for the protein ligand interactions. And in terms of accuracy and general applicability, the systematic molecular fragmentation approach appears to be very attractive. The SMF energy is a sum of two components, abundant and non-abundant energies. And in the SMF approach, the number of abundant fragments scales linearly, where in this formula n is the number of groups, while the number of non-abundant fragments scales quadratically. So the original method is not a linear scaling method. However, to reduce the high cost of non-abundant fragments, Collins introduced a cutoff distance, such as 2 angstrom something. And if the distance between two groups of a non-abundant fragments is less than r cut, then it is treated with the electronic structure theories. If it is larger than r cut, then it is treated classically. So the Collins approach is not a pure quantum mechanical approach. And further, for branched molecules, Collins algorithm yields large size fragments compared to the chain-like linear alkanes. So in this research, to achieve exact linear scaling and to obtain a pure ab initio approach, we completely neglect all long-range non-abundant contributions since they already approach to zero. And we introduce a new fragmentation algorithm for the branch molecules, which yields smaller size fragments compared to the Collins algorithm. And the new linear scaling SMF algorithm denoted by LSSMF have been coded in C++ and integrated with my DF-CCSD module. And LSSMF CC approach such as LSSMF CCSD and CCSD parenthesis T are applied to a series of test cases to demonstrate their efficiency and accuracy. So let me give you a brief recap of the coupled cluster theory. With canonical Hartree-Fock orbitals, CCSD correlation energy can be written in this formula, with this formula. In here, Hn is the normal ordered Hamiltonian and Et is the cluster excitation operator. In here, T. In case of CCSD, it is just sum of T1 and T2. And explicit form of excitation amplitudes are excitation operators given in here. And in here, TIA and TIJAV are the single and double excitation amplitudes. And couple cluster amplitudes are obtained from these equations. And we may also remember the CCSD parenthesis T correction. And parenthesis T correction consists of several terms. The main term is the ET4, and which can be written in this form, in this closed form. In here, Wn is the normal ordered two electron components of the normal ordered Hamiltonian, and Fno is the off-diagonal part of normal ordered Fock matrix. And more explicitly, the parenthesis C correction can be written in this form. It consists of two terms. One of them is coming from the connected, and other one is coming from the disconnected parts. And explicit forms of connected and disconnected amplitudes are provided in here. Now, I would like to talk a little bit about the tensor factorization of integrals, which is central to my DF-OCC module. Approximate factorizations of 4-index 2-electron integrals are becoming increasingly common in modern computational chemistry as a method to both accelerate computations and eliminate the storage or generation cost of the 4-index electron repulsion integrals. One of the popular approximation is density fitting, which is also known as the resolution of the identity, and that the DF approach enables one to express the 4-index 2-electron integrals in terms of the 3-index tensors. In here, let me give you some more details about the density fitting. This is our atomic orbital 2-electron integrals, mu, nu, lambda, sigma. And this is its explicit form. In here, chi, mu are the elements of the members of the primary basis set. In the DF approach, this IO basis array tensor can be written in terms of this 3-index DF factors, and the explicit form of DF factor can be obtained by this equation. In here, mu, nu, p is the 3-index 2-electron integrals, and j, p, q is called as the metric integral. What's important in here, in order to compute metric, we need an auxiliary base set in addition to the primary. Now, I would like to share some result with you. It is a published paper in 2016, and demonstrating the efficiency of our DF-CCSD code. And I have some comparison with the QChem's RI-CCSD. In fact, both codes are producing exactly the same energy, but QChem generally prefer to say RI-CCSD, and we prefer to say as DF-CCSD. In this table, we have the total timings and couple plus CCSD times, number of iterations, and perhaps a more interesting thing is the time per a single CCSD iteration. As we can see, our implementation is quite efficient comparing to the QChem and C4. I can explain the details why it is, but I think we don't have that much time for this. In order to further increase the applicability of our CCSD code, even though DF helps a little bit, but we need to still something new to further extend the applicability. We consider the frozen natural orbitals. We know that virtual space constitutes a large part of the MO space, and cost of CCSD and CCSD parenthesis T is proportional with the 4th power of number of virtuals. The FNOs are defined as the eigenvectors of the VV block of the one particle density matrix, and the occupation numbers are the eigenvalues. We retain the FNOs with the highest occupations in the correlated calculations and treat the rest as frozen. And the virtual block of second order OPDM can be written in this form. In here, TIC, AC are the first order amplitudes. In other words, they are MP2 amplitudes. And then we diagonalize the second order OPDM. In here, T are the eigenvectors. And then after semi-canonization of the FNO basis, we update the MO coefficients by this equation. And in here, V is the new MO coefficients. And the matrix form of the T can be written in this form. Occupied block is just 1, and OV and VO blocks are just 0. and virtual block is equal to the T. After this transformation, and this is the how Fock matrix looks. If we are interested only in energy, we just need to consider the slopes. The OO block and active virtual blocks are already diagonal. Now in this slide, I would like to share some results. In here, the red curve is the timings for our DF-CCSD parenthesis T code, and the green curve is for the FNO implementation. As we can see from this plot, it is obvious that FNO significantly speed up the conventional CCSD. And in fact, for the largest member of the alkane set considered, which is the C10, we obtain almost a 5-time speed up comparing to the DF-CCSD parenthesis T. Now, let's start to the systematic molecular fragmentation. The SMF approach starts with the molecule M divided into different groups. And groups are sets of atoms defined by the SMF algorithm. The basic ideas involved in the method can be illustrated for the simplest case involving a chain-like molecule containing N groups connected by single bonds. Let's represent our molecule by this formula, G1, G2, ... Gn, and each G represents a group. The target is to derive an accurate value for the total electronic energy. So energy of the molecule is a function of the groups. And the energy of the molecule M is determined by summation of the fragment, which are defined in terms of the combination of groups, in terms of the fragment energies. The size of fragments depend on the level of SMF, and the fragments can overlap with each other, since a group can involve in the multiple fragments. Addition of fragments with the negative coefficients are generated to cancel the effects of multiple counting. So we already talked about that the SMF energy consists of two components, the abundant energy and non-abundant energy. The abundant energy can be written by this formula. In here, Fi are the integer coefficients associated with the fragment Fi. For a model system of chain containing 5 groups, the SMF fragmentation scheme can be expressed like this. This is the whole molecule, G1 to G5. Each G represents a methyl group in this case. In level 1, we have this fragmentation, level 2 in here, and in level 3, which means that we need to connect 4 groups to each other, and so on. Thus, the fragment sizes increase with the level used. However, the number of fragments grows linearly with the size of system. The different levels used in SMF are related to some older concept used in the field of theoretical thermochemistry. For example, level 1 reactions are known as isodesmic reactions, level 2 is known as homodesmotic reactions, and level 3 is known as hyperhomodesmotic reactions. Since the abundant energy only includes nearby interactions, one should consider the non-abundant interactions between more distant groups. And the non-abundant interactions may be evaluated by the following equation. And in here, we only consider the allowed fragments. So allowed non-abundant interactions are the interactions that are not already included in abundant energy. For a chain-like alkane molecule with the SMF scheme, the number of abundant and non-abundant fragments are given by these formulas. So what is important in here, the number of non-abundant fragments scales linearly with the number of groups, but number of non-abundant fragments scales quadratically. So the method, original method, is not a linear scaling method. However, we may consider only short-range non-abundant fragments, and their number also scales hopefully linearly with the size of systems. Hence, we may obtain an overall linear scaling approach. So we introduce a non-abundant cutoff tolerance, delta NB. It can be something like the 10 angstrom, 6 angstrom, something. And if the distance between the closest atoms of two groups is larger than delta NB, then this non-bonded fragment is disregarded. And we denote this algorithm by distance-based elimination, DBE. An alternative approach is recommended by Collins and co-workers. In this one, one uses the ratio of distance to the covalent radii, which may be called as the DCRR, and we may calculate the distance tolerance by this formula. In here, XIM denotes the Cartesian position of the atom in the fragment M, and Ri denotes the covalent radius of the atom. And here our LSSMF fragmentation algorithm at first define the level of SMF and tolerances for single, double, triple bonds as well as NB cutoffs. Then read molecular info, and then compute interatomic distances, then compute bond order metrics to determine the bond order between two atoms. Then catch the first non-hydrogen atom. The first such atom is assigned to the group 1, in fact, group 0 in C++. Then assign the remaining non-hydrogen atoms, starting the first non-hydrogen atom, make a loop over atom pairs, ij. If Bij larger than 1, then assign G to the group of the ith atom. Otherwise, assign it to the next group, Gi plus 1. Then catch double, triple bonded non-hydrogen atoms in different groups and match them. Then assign the hydrogen atoms to each group according to the values of the Bij. Then form the group connectivity matrix, LIB. If two groups are connected to each other, then LIB is 1, otherwise it is equal to 0. Further, determine the bonded atoms of the two connected groups. Next, determine the number of hydrogen caps per groups, and then form the bonded and non-bonded domains for each group. Next, form the list of groups and bonded and non-bonded fragments according to the SMF level. And finally, write the micro QC or Psi4 input files for groups, bonded and non-bonded fragments. Micro QC is a new electronic structure software which hasn't been published yet. Once we prepare all input files, and then we can submit all of them simultaneously to our Linux cluster. So this method is naturally parallel. We also need to consider the cap hydrogens in the SMF algorithm. In each final fragment, bonds that are connecting groups in the fragment to other groups that are not in the fragment are called as the missing bonds. And these missing bonds are replaced by bonds to the hydrogen atoms. The total number of hydrogen atoms added to the fragments with a sign of +1 is exactly equal to the number of added to the fragments with a sign of -1. The position of each hydrogen cap is taken to lie along the missing bond vector at a distance which is proportional to the expected ratio of the bond lengths that is calculated by this formula. In here, Xi denotes the Cartesian position of the atom in the fragment, and Xj denotes the Cartesian position of the atom that is not available in the fragment, and Xh is the Cartesian position of the hydrogen cap. Okay. We also developed a new fragmentation algorithm for branch molecules. Our fragmentation algorithm is identical to the one suggested by Dew and Collins for unbranched chain-like molecules. However, in case of branch molecules, we propose a new algorithm. In order to illustrate the difference between two algorithms, let us consider the 2,4-dimethyl heptane molecule. And fragmentation suggested by Dew and Collins yields to this fragmentation scheme at level 3. Please note that in here we have 2 fragments with 5 groups. Normally at level 3 fragmentation for a chain-like molecule, the largest fragment should be as much as including the 4 bodies. But in here it includes the 5 bodies. Okay. Hence, Dewey and Collins algorithm yields fragments at different sizes for chain-like molecules and branch molecules. And we suggest a new algorithm for branch molecules in which smaller size fragments form as in the case of open chain molecules. And our algorithm yields the following bonded fragments for the 2,4 DMH molecule. And this is our fragmentation. And how you obtain this, the logic is this: consider all possible unique combination of 4 groups. And this is the logic behind our fragmentation approach. And in our fragmentation, fragments formed by the combination of 4 groups are called as the main fragments, and the remaining fragments are considered for chemical balance. Hence, we may call them as the neutralizing fragments or renormalization terms reminiscent of the many-body perturbation theory. Our algorithm yields to this fragmentation. In here, F4 means a fragment with 4 groups. Hence, our algorithm yields 6F4 plus 5F3 and 2F2, while Dewey and Collins algorithm yields 2F5 plus F3. Hence, if we compare two algorithms, our algorithm yields smaller sized fragments, but Dewey and Collins algorithm yields a lower number of fragments. However, for high-level coupled cluster computations with large basis sets, the size of a fragment is more important than the number of additional small fragments. And in the case of large groups, sometimes a group can be as small as a methyl group, but sometimes it can be as large as a benzene or naphthalene in aromatic compounds. Therefore, in case of large groups, decreasing the size of fragment from F5 to F4 is still very important to reduce the cost, even though small base sets are employed. Therefore, our algorithm is more efficient in terms of the computational cost and better fits high-level CC methods such as CCSD. Now, I would like to show you some results, and these results obtained for a set of alkanes from the hexane to the decan. We consider all isomers of each species, and we calculate the total energies with the conventional CCSD parenthesis T and with the LSSMF CCSD T and other methods, and obtain the mean absolute errors of the LSSMF approach with respect to their canonical counterparts. And we obtain quite negligible or quite small errors, especially for the LSSMF CCSD parenthesis T, and mean absolute errors are less than 0.6 kcal for considered system. Next, we investigate the effect of non-bonded cutoff, and we plot the error with respect to R-cut. And what we observe is this: R-cut should be chosen as at least as 6 angstrom and so on. Next, we also consider the frozen natural orbital coupled cluster results and try it with different basis sets. Again, we obtain quite negligible errors with respect to canonical FNO methods. And we also note that there is a slight increase in the errors with respect to increasing basis set size.
Sorry, Uğur, you have 3 minutes, okay?
Okay. I am almost done. Okay.
Thank you.
Next, we analyze the effect of levels, and we run calculations with the level 4 and level 5 in addition to the level 3 for the linear case. And we observe that, of course, if you consider larger fragments, an error is significantly decreased. Then we consider a set of polymers for which the polymerization energy at 0 Kelvin per unit is available from the experimental result, but this experimental results are average values. Therefore, we also only consider the average values per unit, and we obtain quite negligible errors with respect to experimental values at LSSMF CCSDT level. Next, we would like to demonstrate the performance of our fragmentation code. And in here, with just a single core and a molecule more than 50,000 atoms can be fragmentized just in 8 minutes. So our fragmentation code is quite efficient. Then, in order to improve the non-bonded contributions we recommend a new non-bonded fragmentation scheme in addition to our new branched alkane scheme. So for the heptane molecule, this is the fragmentation for the bonded energy, and this is the non-bonded fragmentation scheme suggested by Collins. And however, in this one, we only consider two-body interactions. And in order to improve it, we propose a new one in which we consider both two-body, three-body, and four-body interactions, and we obtain much lower energies. Our conclusions for the branched molecules, any fragmentation algorithm which yields smaller size fragments compared with the previous studies has been introduced, and performance of the LSSMF-CC approach have been compared with the canonical versions. Our results demonstrate that the LSSMF approach introduced negligible errors compared with the canonical methods for the test sets considered, and a similar performance has been observed in case of FNO-CC methods. And to demonstrate the applicability of our approach, we consider a molecule with more than 10,000 atoms. And at the LSSMF-CCSD parentheses TCC PVTZ level, the energy computation on a Linux cluster with 100 nodes, and each of them, including the 4 cores, is performed just in 24 hours. If we would this calculation with a canonical CCSD approach, it would include more than 193,000 basis functions. So overall, we conclude that LSSMF-CC approach are very promising for accurate computation of molecular properties in macromolecular systems. And all these computations are performed with our new molecular integrals library, which is called as the Molin framework. And it just appeared in the CAN archive. And finally, I would like to thank to the Scientific and Technological Research Council of Turkey and Ms. Betül Ermiş of Department of Chemistry, Hacettepe University. And thank you for your attention.
Thank you very much for the interesting talk. And now we have time for questions, comments. Okay, Uğur, did you consider working on iterative variants like -1, for example, using this formulation?
Presently, we only consider the non-iterative parenthesis T, but we will be interested to consider full T or some other iterative versions of the parenthesis T contributions.
Okay, I see. Maybe questions, comments? If not, just a second. Did you already test your method for chemical reactions? From Alessandro Genoni question.
We tested, yes, for a range of alkane molecules. We compare for the isomerization energies, and for the test that we considered, we obtained quite negligible errors. Yeah.
Okay.
And there are lots of results published by the Collins. There are lots of such benchmarkings.
Okay. Thank you very much for your talk.
You are welcome.